Hi, James.
I can't quite hear you.
Hello.
Oh, there you go. Yeah.
All right. How's it going?
Oh, pretty good.
That's good to hear.
How about you?
I'm all right. I'm in Cleveland. We got a little bit of snow, but not too much. I think like 8 inches. How much did you guys have?
I think it was like a little bit over 11 or something.
Oh, wow. Is that a lot for Salt Lake City?
Yeah, it was like the seventh highest total ever
Oh,
or
man.
something.
I'm surprised to hear that. In Cleveland, we have like at least once a year, we have at least a foot of snow, but
Hmm.
usually more than once.
Yeah, this was the most within like 24 hours
Oh, I
stuff for
see.
here.
Just within 24 hours.
Hmm. Oh, and then I was looking a bit at the discussion slides and I was thinking to probably skip over the first two
Okay.
just to jump into the set problems,
All right.
you know? Um, since they just had the quiz on proofs and stuff.
All right. I can do that.
And then if we have time, we could always go back.
Hi, everyone. We're doing more problems, as we always do. And the first one is on the screen now. So take a couple minutes to look at it and write something down, and then we'll discuss it. All right, so I hope you've had some time to look at that problem. And would anyone like to either type in the chat or shout out one element that they think is in A intersection B union C? And then we'll start by checking it, and then we'll write out the remainder. So Colton says 8. So let's check 8. So first of all, Colton notices that 8 is a multiple of 4. So 8 equals 4 times 2. And so 8 is in set A. So that's good. Now, because it must be in A, because it needs to be in A intersection B union C. So next we need to check that 8 is in B union C. So it either needs to be in B or C. So we can just check one of them. That would be sufficient. And so we can just check C, for example, and we see that 8 squared is 64, which is clearly smaller than 1,000. And so 8 is in C. So 8 is in A, and 8 is, so this implies that, let me just write this. This implies 8 is in A, and this implies that 8 is in C. Okay, so therefore 8 is in A intersection B union C. So we have to find 4 more that's intersection B union C. We have to find 4 more numbers, and Annika has one, 16. And so we're just going to go through the same process. So 16 is a multiple of 4. 16 equals 4 times 4. So that means that that 16, it's a positive multiple of 4, so therefore it's an A. So it's an A. All right. And then it either needs to be in B or C in order for 16 to be in A intersection B union C. So again, we could check that it's in B this time. So 32 is equal to oh, actually, no. This number is not in C, so it's not in B. So we can only check that it's in C, and it is in C because 16 squared is, I think, 256, and that's much smaller than 1,000. So 16 is in C. So therefore, 16 is in A intersection B union C. And then we could do that for 3 additional numbers. For example, we can do it for 4. We could have also done it for 12. So you can verify that 4 is in A, and that 4 is in C, and that 12 is in A, and that 12 is in C. And then we can also do it for 20. So, yeah. So that would give us 5 numbers that are in A intersection B union C. Are there any questions or comments or concerns about this question? All right. Here's the next one. Use Venn diagrams to verify the following property of set operations. A intersection A union B is equal to A. So take a couple minutes and then we'll do it. Okay, if there's anyone who would like to, I think you can draw on the screen. So if someone is interested in sharing their work for this problem, then you can go ahead and get it started and start to take us through your strategy. If not, I can do it, but I mean, if not, I can start it. But if someone would like to, please, you can go ahead. All right. Then I'll get it started here. So we want to verify that A intersection A union B is equal to A, and we're asked to do it using Venn diagram. So we're going to write out the left-hand side using a Venn diagram and show that the region that we get is just A. That's how we'll verify. So let's make a box. And then we're going to have two sets, A and B, inside the box. The box is our universe, so you can call this the universe. That's the box. And we have a set A in the box, in the universe, and another set B. And now we're going to fill in the region that is A intersection A union B. So first, let's fill in the region that is A union B. Does anybody just want to shout it out? What region would be? It might be hard to describe, but if you want to shout it out, what's A union B here? What should I shade in?
Both circles?
Yep, that's right. A union B. What that means is that, so if an element is in A union B, if and only if that element is in A or it is in B. So A union B is is all of the circles. So all of the shaded region. That represents being in A or in B. All right. And then, so we know that in order to be in this set, then we have to be in A union B. So in order for an element X to be in this set, that element has to be in A union B. That element also has to be in A because it's the intersection. So, so we also need to shade in A, and so let's do that as well. So, sorry, let's make this set A and let's make this set B. So this is A, this circle was A, this circle is B. A intersection A union B is going to be where A intersects with A union B. We just shaded in what A union B is. So now we're going to shade in what A is. And where they overlap, that's going to be A intersection A union B. So we're going to shade in A. Let's see here what happens. Okay. All right, so what we're left with, so what we've, where we've shaded in both directions, that's the intersection. And so you'll notice that what we've shaded in both directions is exactly A. So, so therefore A intersection A union B is equal to A. And this isn't really a proof. We could do a proof which is a little bit more rigorous, but this is, it asks us to make a Venn diagram, so that's why we did it. But I mean, it's for such a for a problem like this, using a Venn diagram is sufficient. But but I don't know. I wouldn't call this exactly a formal proof, but um, but it was what we are asked to do. It says to make a Venn diagram to show that A intersection A union B is A, and so we did that because we shaded in A union B, we shaded in A, and then we intersected the two, and that happens to be A. So, are there any questions or concerns about this problem? All right, let's take a look at another one. I think, yeah, this is the next problem. All right, so take a couple minutes and then we'll discuss it. All right, would anyone like, if you would like, you're welcome to start this problem. Um, you would be able to write, I think, on this screen. So if anyone is interested in sharing their approach, then you can go ahead. All right, so I'll start this one. So it says use the Venn diagrams to check whether or not you believe the following property is true. And if it is not true, give a counterexample. So in order to compare the left-hand side and the right-hand side, we're going to make a Venn diagram and see if the regions that are created by the two sets are the same. And if they're, well, what we want to check is that the region on the left-hand side, if this is a true statement, then the region on the left-hand side should be contained in the region on the right-hand side. So that's what we're going to check. And if that's not true, then we should, if the Venn diagram doesn't give us that information, then we'll come up with a counterexample. So we'll actually come up with actual sets A, B, and C, such that the left-hand side is not a subset of the right-hand side. But to begin with, we'll make these Venn diagrams and check if the left-hand side is a subset of the right-hand side. So all right, here is A. That's A. And then this is B. Okay. And then this will be B. And then here's C. Okay. And then all of these sets, they're sitting in some universe, some bigger world. For example, the universe might be the real numbers, and these three sets, A, B, and C, might be subsets of the real numbers. Or this might be, universe might be the plane, R2, and then these sets would be subsets of the plane. All right, anyway, so let's start to write out the left-hand side. So we'll start by writing out A without B. So that's this. Oh, okay. That's this set. Right, so we took the A without B, that's A minus B, that's the part of A that is not in B. So we shaded in everything except this piece here, which is in B. All right, then B without C. So similar idea here. So we're going to shade in the part of B that does not involve C. So that's this. All right, and then it's the left-hand side is the union of these two sets. So everything that has these diagonals, that entire region is now the left-hand side. What's up, Mike?
So I noticed on A minus B, you covered up the portion that's containing C as well, but in B minus C, you didn't like draw the lines inside the
yes
portion between A and B.
Thank you. Yeah. So this region here is part of B without C, as Mike points out. It's the intersection of B with A, which it is not including C. So it's a part of B without C. Thank you, Mike. So this is the union of A without B, union B without C. And so now we want to draw the right-hand side. The right-hand side is A without C. So I'll draw the diagonals in a different direction. So let's see here. So, A without, oh boy. Hold on a second. Oh, okay. All right, that's fine. We're going back here. So no, with regard to Kyle's question, you don't have to, I don't think you have to say that there's some universe, but sets are always a subset of some larger universe, some larger set. So it's something to be aware of, but you don't have to write that out. So anyway, so we're putting in A without C, which is going to be the right-hand side now. So A without C is this. So it's all of A, but not including C. So let's see here. Okay. So those diagonals going downward, that's the right-hand side, and the diagonals going upward, that's the left-hand side. And then we want to ask the question, is the left-hand side a subset of the right-hand side? So it's clear now that that is not the case. There's region, there's parts of the left-hand side which are not a subset of the right-hand side. So this gives us the intuition that the left-hand side is not a subset of the right-hand side. So the next part of the problem then is to find a counterexample. So there's a lot of ways to do this. Does anyone want to share a counterexample that they have in mind? So Colton says A union C, and maybe the questions, it's not super clear. So what we mean by a counterexample is a collection of sets such that this set is not a subset of the right-hand side. So so for example, you can take A equal to 1, B equal to 2, and C equal to 3. And now what we want to verify is that that there are elements that are in the left-hand side which are not in the right-hand side. So in this case, A without B. What is A without B? Well, it's 1 without 2, so it's just 1. So A without B, we're just writing out the left-hand side. The left-hand side. So that's A without B, and that's union B without C. And that, oops, just getting parentheses in here. So the A without B is just going to be 1 because it's 1 without 2. So 2's not in A, so that's just A itself. So that's just 1 union B without C. So 2 without 3, well, 3 is not in B, so this is just 2. So that's 1 union 2. So that means that the left-hand side is just 1, 2. And then A without C, so that's the right-hand side, that's the right-hand side, A without C. So that's 3 without 1, sorry, it's 1 without 3. 1 without 3, so that's just going to be 1. So, okay. So what we have is that the left-hand side contains 2, and the right-hand side does not. So that's our counterexample. So we've now shown that we have 3 sets that exist in the. We found 3 sets such that the set on the left-hand side is not a subset of the set on the right because 2 is in the left-hand side, and it's not in the right-hand side. If this statement was true, then for every single set, for every triplet of sets A, B, and C, it would be true that the left-hand side would always be contained in the right-hand side. But here we have an A, B, and a C where that is not true. There now exists an element in the left-hand side, which is not an element in the right. Are there any questions about that? Hi, Mike. Yeah, what's up?
So I'm just curious on the left-hand side in particular. So A minus B union B minus C.
Mm-hmm.
So when you're attributing values to them, my brain just like automatically goes to arithmetic. So it's a minus b, so 1 minus 2. How do we just resolve with just having 1 instead of not incorporating b at that point?
Okay, so the issue here is that we're now dealing with sets and not numbers. So these are sets, and when we put a minus in between two sets, it has a different meaning than when we put a minus in between two numbers. So in particular, I think this is written down somewhere in the notes, but what we mean by a minus b when we're talking about sets, because a and b are now their sets, a minus b is equal to a intersection with the complement of b. So I think that you guys I think we write that down with a prime in this class. So so when we talk, so a minus b is an intersection of sets now. It's what's in common between two sets. And in our example, a is equal to 1 and b is equal to 2. So if the universe is equal to 1, 2, and 3, then b complement, which is this b prime thing, b prime is the universe. It's what's in the universe that's not in B. And what's in the universe that's not in B is 1 and 3. So B complement, or B prime as we've written it, is just 1 and 3. And so now we're taking the intersection of B prime with A, and the only thing in common between B prime and A is 1. And so that's why A without B, A minus B is just the set containing 1.
That makes a lot more sense. Thank you.
All right, let's move on to the next one. Okay. So take some time to think about it and then we'll discuss. All right. Does anyone want to, if you would like to type in the chat or shout out what B intersection C is, then go for it. So Annika has the answer to the whole problem written out there. And so, yes, let's start with what B intersection C is. So B intersection C is what's common to B and C. So the only two elements, as Annika observes, that are common to B and C are 1 and 2. So B intersection C is equal to 1, 2. And then for the second part of the problem, we have this notation, we want to find the power set. So actually just taking a step back, if you're ever asked during a problem anywhere to find the power set of a set, the first thing you should do is figure out what the set is composed of. What does the set look like? So the set that we're interested in finding the power set of is B intersection C. So we ought to find B intersection C first, and that's why we did that. So we now have B intersection C, and we can find the power set. The power set is the collection of subsets of B intersection C. That's what the power set is. So the first one that Annika has written down here is 1, 2. So 1, 2 is indeed a subset of B intersection C. It's equal to B intersection C, and it is a subset as well. And the next one is 1. So 1 is a subset of 1, 2. So that's right as well. And then that's a 1. Then the next one is 2. 2 is a subset of 1, 2. And so is the empty set. So I'm not exact, I think maybe this is the notation that you guys are using for the empty set. There's other ways to write down the empty set that you'll see, and maybe we do in this class or not sure. You might see that for the empty set as well. But these are the 4 subsets of B intersection C. So the power set asks us to find, when we want to find the power set, we want to find all subsets of the set. Our set is B intersection C, and so we've written down all subsets. Yeah, that's this one. Are there any concerns, confusions about anything? If there are, just shout them out or type them in the chat. I'll wait just a couple of maybe 30 seconds, just in case any of you guys have any questions before we move on. All right, here is the next one. So take a little bit of time to get this one started, and then we'll get going on it. All right, for part A, does anyone have any thoughts, or are they anyone certain about the answer, or want to shout out what they think might the answer might be? All right, so we want to know if A cross C is a subset of B cross C when A is a subset of B. So it doesn't say to prove this statement, but it's just going to be a little bit easier to just kind of do this a little bit more formally. So we're going to take an element which is in A cross C, and we want to check whether it's in B cross C. That would verify that A cross C is a subset of B cross C. So let's take an element that's in A cross C. So let's let X be in A cross C. So what that means, yeah, this is a big X. What that means is that X is equal, since X is in A cross C, X is equal to A1, A2. So it's an ordered pair such that A1 is in A, and A2 is in B. Sorry, C. It's A cross C. So A cross C is the collection of ordered pairs where the first member of the ordered pair is in A and the second member of the ordered pair is in C. So here we've just taken an element, call it big X, in A cross C, and we've said, well, what does it mean that it's in A cross C? It means that it's an ordered pair with the first element in A and the second element in C, and we've just labeled them A1 and A2. So now we observe that A is a subset of B. So that means that if A1 is in A, then A1 is in B. What does that say before A? What is it? Oh, I think this is such that. So this means such that. ST is such that. Yep. Okay, so A1 is in A and A is a subset of B. So A1 is in B. All right, so now we have that A1 is in B and A2 is in C, and X is A1, A2. So X is an ordered pair where its first coordinate is in B and its second coordinate is in C. So therefore, thus, X is a member of B cross C. So we've just shown that for an arbitrary member of A cross C, it is a member of B cross C. Therefore, every element of A cross C is a member of B cross C, and so A cross C is a subset of B cross C. So A is this is true. So that's true. For the second one, are there any concerns or questions or comments about part A? Okay. For the next one, it says for all sets A and B, A union B cross A minus B is equal to A squared minus B squared. All right. So one thing that you guys have learned, I think, in class is that, so if you write out what this set is, A squared minus B squared, we can rewrite it. Let's say that the universe is, or we don't have to do that. We can write it as a squared intersection with the complement of b squared. And then we can recognize that this is a subset. This is a subset of a squared. So this is a property of sets that if you have two sets, just going to call them T and Q, then T intersection Q is a subset of T. It's also a subset of Q. Okay. So we can prove that. It's not hard to show, but for now we're, maybe you guys proved it in class, I'm not exactly sure, but it's true. So that means that a squared intersection b squared complement is a subset of a squared. So that means that the right-hand side is a subset of a squared. The left-hand side, well, if there was an element that was in B that was not in A, and we took that element and we made it the first entry in an ordered pair. So let's say that there's an element in B that's not in A, and let's call that element Q. So Q is in B minus A. So therefore Q is in B, as we've just, Q is in B. It's in B without A, so it's in B. It's also not in A. Now, if there is an element that's in A that's not in B, let's call that element little b. So little b is in A, but it's not in B. Okay. So this element AB, this ordered pair, little a, little b, well, that's in the left-hand side. It's in the left-hand side because little a, actually, I think I made that a Q. It's fine. This first element in the ordered pair is in B without A. Well, that means that it's in B, and therefore it's in A union B. So the first element is in A union B, and the second element, which we called little b is in A without B. So therefore, this ordered pair is in the left-hand side. But observe that it cannot be in the right-hand side, because the right-hand side is a subset of A squared. And remember that A squared is equal to A cross A. So that means that Q, well, Q is not in A, and so the first entry of this ordered pair is not in A, and therefore this ordered pair is not in A cross A. So we've just found, or we understand how we could find a counterexample now to show that these two sets are not equal. In particular, we would want to make two sets A and B, and we would want to ensure that there was one element which was in B that was not in A, and an element that was in A that was not in B. So for example, we could make A equal to 1 and B equal to 2. So then the element, not and B equal to 2. Then the element 2, 2 is in B, it's not in A, so we could set Q equal to 2. And there's an element little b that's in A and it's not in B, and that's 1. So this would be 1. So then the ordered pair would become 2, 1. And that this ordered pair 2, 1, it would be it would be in the left-hand side, but it wouldn't be in the right-hand side for the reasons that we just described. So I think our time is up. If anyone has any questions, please ask them. Yeah, but that's all for the day. Also, the discussion slides get posted on Canvas, so as extra study material, it could be, it's a good idea to go ahead and review the remaining questions if you have time to do that.
Thank you.